Consider a body of mass m that falls freely from a height y1 above some arbitrary reference level to a height y2. The force of gravity, W, is equal to mg, is the only force acting on that body. So we're neglecting air resistance. We're also assuming here that the body stays close to the surface of the Earth, and so the gravitational force remains constant. When changes in height are large, we would need to take into account the variation in the gravitational force with distance, but we don't need to worry about that here. The direction of the gravitational force, W, is in the same direction as the displacement, and so the work done by gravity is positive. And it is equal to the force times the distance moved, which is equal to mg into y1 minus y2, or mg y1 minus mg y2. Note that if the block had been moving in the opposite direction, then the work done would have been negative. This equation shows that the work done by gravity can be expressed in terms of the value of the quantity mgy at the beginning and end of the displacement. And this quantity mgy is known as the gravitational potential energy, and it may be considered as the energy stored in the body due to its position. The body has the ability or the potential to do work if it has potential energy. For example, a hammerhead being dropped onto a block of metal will do work on the metal by compressing it, hence the name potential energy. So gravitational potential energy, which we will denote by U, is equal to mgy, and in this case the initial value U1 is equal to mgy1 and the final value is equal to U2 equals mgy2. And therefore the change in the potential energy, delta U, which is defined to be the final value minus the initial value, is equal to U2 minus U1. And therefore, since the work done by gravity is equal to U1 minus U2, it follows that the work done by gravity is equal to minus U2 minus U1, which is minus delta U. So in other words, the work done by gravity is equal to minus the change in the gravitational potential energy. So when a body moves down, the work done by gravity is positive and the gravitational potential energy of the body decreases. If, on the other hand, a body moves up, the work done by gravity is negative, and so the gravitational potential energy increases. Now let the body's speed at point y1 be v1, and at the point y2 let it be v2. The work energy theorem says that the total work done on a body is equal to the change in the kinetic energy of the body. In other words, the total work done, W total, is equal to the change in the kinetic energy, K2 minus K1. If gravity is the only force acting, then the total work done is equal to the work done by gravity, which is equal to minus delta U, which equals U1 minus U2. And combining these two equations, we get that delta K is equal to minus delta U, or K2 minus K1 is equal to U1 minus U2. Rearranging that, we get K1 plus U1 is equal to K2 plus U2. Or in other words, a half mv1 squared plus mgy1 is equal to a half mv2 squared plus mgy2. We now define the sum of the kinetic energy plus the potential energy, K plus U, to be the total mechanical energy of the system. And by system here, we mean the body and the earth, because as I mentioned at the beginning of this section, gravitational potential energy is a shared property of both bodies. It follows that when gravity is the only force acting, the total mechanical energy of the system remains constant. In the case of our falling body, the initial potential energy is converted into kinetic energy, but the total mechanical energy remains constant. Note also that it doesn't matter what height we choose to be our origin, in other words, the zero of potential energy. This is arbitrary. The change in potential energy will be the same whatever the choice of origin is.